बच्चों सत श्री अकाल and namaste from my side. So hi everyone. So this is Indrajeet Singh, your own physics educator, welcoming you all to the most sensible platform of an edtech. Right? Okay, for the aspirants, those who are preparing for JEE and NET kind of examinations. Hi, for you all. So guys, as usual, this is the sixth lecture of KVPY series. Right, the exam that is going to happen on 9th of January 2022. Before this series, we had a poll. Right, we asked you what are your requirements. Right, majority of the students right polled for the series on the KVPY session, and we did. We planned. Right, we were having very less amount of the time, and in that case, we need to cover theories also and questions also. But anyhow, right, on your demand, we planned and brought this series, and successfully we have completed 5 lectures in physics. The lecture 1 started with the units and dimensions, right, followed by kinematics, motion in 1D and 2D, right, right, crossing from work energy power, reaching up to the rotational motion that was our previous session, and now we have reached to the concepts of thermodynamics and thermal physics. So, the major issue we faced while researching, right, that what kind of the session, what should be included in all of in the series, right? So the major issue we felt, especially in physics, right, it was how we can cover all of those questions and theoretical part into the very less amount of the time. So it means that we were having less time and we have to cover a lot. So at that time, we decided to follow the reverse engineering. In my previous sessions also, in all of my sessions, I used to discuss about this previous engineering. This is the actual the flow of the chapter, how we are going to deal with that. Right? First, one question will appear in front of you. I will give you the minute to solve. After that, we are going to discuss the solution for this specific question, and we are going to see what fundamental concept is actually included in that and why. As I said before, the entire physics depends on why and suppose. As I said before, the entire physics depends on why and suppose, and we are going to see with that. Right? So, hope so you all are ready, guys. Just before planes take off, we are used to having safety instructions. Okay, it's type of seat pad indication. So, it's the same thing I want to tell you in front of you all. Right? Just check your seat belts. This session is going to be quite exciting, really. Right? In very less amount of the time, we are selecting those topics, right? Those who are quite important from the KVPY point of view, right? And we have combined. If you see now previous lecture, we combined 1D and 2D because it was important, and then the rectilinear motion was more important, right? After that, we kept a separate lecture of NLM because mechanics should be mechanics should be represented in that way only. So whatever the things come in front of you all, right? It takes an enormous amount of the research and time. Okay. Kindly, thanks a lot. You've given an awesome response into our previous sessions. Okay. And now obviously in this session also thanks a lot that you are cooperating and you are seeing this and spending some quality time with us. Okay. So now let's move on to the most important part. Aha! Session of Indrajeet never begins without a fun element. Or always begins. Never begins or always begins. Yes, always begins with the fun element. Right? Because as you all are, what you can say, completely scared of physics. Some of the students might be completely scared of physics. Right? Alex tried a lot. Right? Alex tried a lot. And he is even like applying his continuous efforts. Right? But still, some percentage of the students are still, right? Feeling scared. They used to get scared. So don't get worried. We will remove that fear. Okay. See, while dealing with the laws of the thermodynamics, something like that. And this just for fun. Please don't take it seriously. I'm not disclaimer. Please don't take it seriously. Right. Okay. Dealing with the concepts of the thermodynamics and thermal physics is like that. While entering a warm air, yes, I'm prepared. I'm prepared to take the soul stone, but we are completely unaware of what amount of the sacrifice we have to give. Right? He wasn't aware. He reached to the war, he got a specific thing where soul stone is there. he reached to the warming, right? Hydra was there in front, okay? He said you have to sacrifice one soul to get the soul stone. So we are aware, right? From we are prepared, but we are not aware of what sacrifice we have to do. The same feeling you will deal, the same feeling you will have, sorry, right, while dealing with the concepts of the thermodynamics. You all are aware, yes, we want to do it. But at some point of time, at some point of while solving, at some point while solving those questions, you get completely stuck. And you have to really sacrifice the enormous amount of it. Okay. So guys, let's begin this session. It was just a fun element, guys. Please don't take seriously. In this chapter, we are going to cover all of those stuff: thermal physics, thermodynamics, and Kinetic. Right? If possible, we will try to cover this because it's having the very limited amount of the concepts, right? Like mean free path and everything. So we are not going to deal that much with the kinetic theory of gases, right? Okay, because since years, right, only 1 to 2 questions have been. So I think the rest of the part we are going to cover. Now let's move on to the flow of chapter. Okay, just we are going to take some amount of the time, right? I'm going to discuss the flow of the chapter rapidly, okay, and then we're going to see the first question of this session. Now, one side it is thermodynamics. If I'm talking about thermodynamics, then there are enormous concepts, right? The first one, okay, we used to discuss with the zeroth law of thermodynamics. Right? After that, we used to discuss the definition of what is delta Q, what is delta U, and what is delta W. After that, we used to discuss with the first law of thermodynamics. Right? After that, we used to discuss the thermodynamics processes, right? Like isobaric process and everything. After that, we used to discuss with the work done of all of those stuff, right? For all of those processes and the relevant graph. Right? After that, we used to deal with the second law of thermodynamics, right? And the relevant statements. Second, the heat engine, heat pump, right? Heat engine, heat pump, and finally the Carnot engine and the relevant graph and their efficiency. So this was one of the things, right? We always used to go with the thermodynamics, right? Maximum things we will try to cover. And if I'm talking about the thermal physics or heat transfer, right? Generally, thermal physics it means right now I'm talking about the heat transfer, right? In many of the resources they are having the multiple names. Okay, one part of the thermal physics moves on to the radiation, right? One part of the thermal physics moves on to the radiation. One part of the thermal physics moves on to the radiation. Okay, first part. Radiation contains Stephen's law, right? Wave displacement law, Kirchhoff law, right? Emissivity, absorptivity, absorption power, reflectant power, emissive power, emissivity, spectral emissive power. This all of those things we are going to discuss. You always used to see into the radiation part. Right? Now, the first part of the thermal physics completely moves on to what? The specific heat, latent heat, what is the heat supply? We used to with C, CV, right? CP, what is the latent heat, right? That's temperature versus time graph. Okay, temperature versus time graph. Temperature scales we used to see, right? Temperature scales we used to see. The most important thing from the competitive examinations point of view, that is principle of calorimetry, heat loss is equal to heat gain, right? All of these things, right, we used to see. Okay, principle of calorimetry, right? Joule's law and everything. Okay. What is the heat supply? Q, right? Okay. How much amount of the heat is needed to increase that much amount of the right temperature of the substances, kind of the things. And apart from that, one remaining part, okay, the rate of the heat flow dq by dt. We used to deal with this, right? Second, series and parallel combination, right, of the right series and parallel combination. Okay, like this way. I'm extremely sorry. Okay, series and parallel, right, for this rate of heat flow, and the concept of thermal resistance, right? with this concept of thermal resistance, series and parallel of the thermal resistance, right? With this concept of thermal resistance, series and parallel, and obviously the expansion of solids, it remained. Okay, linear expansion, right? Okay, linear and like alpha, beta, and gamma. This three. So this is what entire part, right? I'm not talking about that it is right depicted completely into the detailed format, but whatever the maximum amount of the things, right? I kept in front of you, right? Because it is not a detailed lecture, right? It is only the one shot, right? So maximum things I kept in front of you, okay? So if you want to take a screenshot for this specific point, I'm moving aside and giving you the 5 seconds to snap it, right? Come on, everyone. So it's 5, 4, 3, 2, 1, and that's it. So this was a flow of chapter, right? And why I started giving this flow of chapter from the rotation, because there exists in future, right? In my future sessions, right? Okay, some of the topics or some of the chapters will come, right? Some of the chapters will come, and those who are really in need of giving it this flow to you all, right? This flow will really help to deal with all of those chapters, right? So now let's move on to the very first question of this specific. As usual, you all are aware of, right? We are going to deal with the reverse engineering, right? We are going to deal with the reverse engineering slowly, right? We are going to deal with the concepts, right? And after that, we are going to see the solution, giving you all a minute, seeing the solution as usual, and we'll see the what fundamental logic it is being used in this. Okay, so now, if the temperature of the sun were increased from T to 2T, so this was visual, it is kept in front. It is for sun. Right? Visual is kept in front of you, it is for sun. Temperature is increasing from T to 2T and radius is increasing from R to 2R. Then what will be the radiant energy received on the earth to what it was previously? After changing in temperature and after changing into the dimensions, the radius, right? What will be the ratio of the new energy to the previous one? Yes, now the ratio of the new radiant energy received towards the earth. This one. Simple law we have to use, right? This question is quite easy. You have to just use one single law, right? Replace all of those values, whatever it is given into the question, and you have to reach up to answer. This is the first question of this session, right? And this could be quite easy. So let's give you all a minute to solve this, right? Okay, come on everyone. When here your countdown starts. Okay, come on everyone, guys. As usual, I used to say in all of my session, right? It is not important to give right answer or wrong answer, right? Physics is all about interaction and participation, right? Okay, it is all about interaction and participation. You have to interact, you have to participate. Otherwise, you will be like an ideal person into the crowd, right? Okay, an odd in the crowd. Okay, it will be like an odd in the crowd. Come on, less than half time is remaining. Okay, it's a very simple thing. One law, you have to apply it directly and get the answers. Okay, and after this, we are going to discuss some 1 to 2 laws related to the radiation into the heat transfer. Now, less than 15 seconds remaining. Very simple thing. One visual is also there in front of you, and that will help you a lot. Okay, radius is changing from R, right? Radius is changing from R to R. Right. Radius is changing from R to R. Temperature is changing from T to radius is changing from R to 2R. Temperature is changing from T to 2T. Right. The same thing happens here, na? Okay. Now. So we need to find the relation between the energy and temperature. Right. In question, data related to the temperature and the radius of any specific about the sun it is given, and we have to reach up to energy. Right. Data about the temperature it is given, and we have to reach up to the energy. Right. So for this, we are having only one way, right? That to use the Stephen's law. Right? To use the Stephen's law. what this law states, we are going to discuss it in a very few minutes after, right, providing you all the solution of this question, right. First of all, we are going to discuss the solution, and after that we will discuss, right, the Stephen's law in a bit detail manner. Now, this law states that energy per unit area per unit time, right, it is directly proportional, or you can say removing the proportionality sign. Okay. This is an actual equation of this Stephen's law for all bodies. Right? Basically, there are two equations. One is for the black body and rest is for all. This is the general equation for the Stephen's law. Now, talking about energy per second. So it means I am taking t is equal to 1 second. So energy received, it is directly proportional to what? Okay, see now. Square t to the power 4. Why? Because area is directly proportional to. So this equation we are going to use. Right? This equation we are going to use and solve this. Okay, now see. Previously, energy was even. After changing into the parameters, energy got equal. So here it was R1 square T1 whole to the power 4, R2 square T2 whole to the power. Now, the radius is changing from R2 to R. So E1 by E2, that will be equivalent to R square by 2R square. Right? Not 2R square. Right? It is 4R square. Okay? It is 4R square. The temperature is changing from T to 2T. So it is 16 T to the power 4. Okay, this is gonna get cancelled, right? And we are going to get E2 will be 64 times of E. Right? E2 will be 64 times of. Right? So what will be the ratio of E2 by E1? That will be 64. So if the dimensions of the radius of the sun is getting changed, right, then the amount of the energy Earth is receiving now, that is 64 times the previous one. After changing into the parameters, whatever the amount of the energy Earth is receiving, whatever the amount of the energy Earth is receiving, it is 64 times the previous. 64 times the previous. Right? What will be our answer? The D will be the perfect answer for this specific. Now, what theory we got from this question? What fundamental logic we got from this question? Let's deal with that. Right? See, as usual, I used to say we are not dealing with any quantitative approach, that we are having the 2 hours of the lecture, right, and we are going to solve. Okay, we are not dealing with a quantitative approach, right, that 2 hours of the lecture we are having and we are going to solve 20-25 questions. No, solving maximum amount of the question, it is not important right now. Okay, rather than to clear out your basics, because KVPY completely, right, this kind of the examination always they checks your basics. And how fundamentally strong you are, how you are having the command over your. So, Stephen's law, what it states, okay, you have seen into the many resources, right? In many resources you have seen about the Stephen's law, right? In many of the resources you have seen about the Stephen's law. Now, what it states, right? It states energy received per unit area per unit time is directly proportional to the fourth power of the temperature. Right. If I'm talking energy unit received per second or energy radiant energy per second, that is E by A, right, directly proportional to T to the power 4. Removing the proportionality sign, I am getting sigma A T to the power 4, where sigma it is Stephen's constant having the value of 5.67 into 10 to the power minus 11. But this is not an actual statement of the Stephen's law. Right? This is especially for black body. Right? This is especially for black body. Now, what will be the general statement? And that includes the emissivity. The energy, that is emissivity sigma A T to the power. This emissivity find how body is. This E will define whether it is a good observer or not. Absorber, sorry, not observer, absorber or not. For black body, we are taking E is equal to 1. Right? For black body, we are taking what? Right? E is equal to 1. Similarly, right, with Stephen's law, there exists another law that is known as Wein's displacement law. Right? Wein's displacement law. Now, what it states? Wein's displacement law. What it states? It states that suppose this is an object that is having the surface temperature T. Now it is releasing some amount of the radiations, yes, lambda. It is releasing some amount of the radiations having wavelength lambda. So that emitted wavelength is inversely proportional to the surface temperature. Inversely proportional to the surface temperature. Right? This is what the Wein's displacement law is. Right? And the third law in the radiation part is Kirchhoff law. Right? Third, right? Okay, it is the Kirchhoff law. A by E ratio is constant. Right? But this much, it is not having as much important as what we are thinking. It is quite simple. Okay. Don't get so much worried about it. Don't get so much worried about it. Statement. See, these two things are important, right? From the question's point of view. Right? Kirchhoff law is there, spectral emissive power is there, emissive power is there, emissivity definition is there, reflectance power is there, absorptive power is there. We are also having the another relation of R plus A plus T that is equal to 1, where R is the reflectance power, right? R is the reflectance power, right? A is an absorptive power. Many things are there, right? Okay, and T will be the transmittance power. Many things are there, but we are not going to move on with that part, right? Because otherwise the lecture will be quite detailed. Okay, lecture will be quite detailed. Okay, so this is the stuff we got from this question. And what was the answer? 64. Let's move on to the next question of this specific session. Now, this question contains two concepts, right? And it is they are really helpful, right? So, first, what will happen if we are increasing the temperature of the object? Now, here comes the awesome concept, a very sensible concept of expansion of solids, right? Expansion of solids when temperature is either increase or decrease. Expands on increasing, right? And obviously, with minimal amount they compress. Right? Not completely to the regain its original position, but they used to compress by some amount, right? When temperature decreases, right? So this question is quite awesome, right? Because this question is a combination of equation of pendulum, and we can correlate that time period of the pendulum with. Right? Generally, we have seen the time period of the pendulum equation, right? We have seen the expansions of the solid. There's two different concepts we have already seen. Now we are going to merge it and then create a new one, and create a really new awesome. Okay, so let's deal with it. A pendulum clock loses 12 seconds a day if temperature is 40 degree and gains 4 seconds a day if temperature is 20. A pendulum clock loses 12 seconds a day if the temperature is 40 and it gains 4 seconds a day if temperature is 20. See, it's a very, very simple thing. If I am talking about the room temperature, then we are having, let us take an example, the intermediate temperature is room. Suppose, I'm not saying the answer is approximately nearly equivalent to the room, no. All are equivalent, the two options are equivalent to room only, room temperature only. But I think let us assume that the time period of the pendulum is exactly T. You see the pendulum, na? Like this. Tang, 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 tang. Right? Whenever you used to hear this word pendulum, na? Right? Whenever we used to hear this word pendulum, right? So we used to hear from a voice from our inner side, right? What it says, dang, 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 right? Like this. So the same pendulum. Suppose you are keeping. Suppose I'm keeping the pendulum at the this is the room temperature. Okay, it's nice, nice. Okay, you know, tung, 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 tung. Exact. I'm having the time period. Take. Suppose the temperature of the room will increase to 30%. Now the pendulum will. Oh, I lost my important 12 seconds. Time is money, right? I lost my important 12 seconds. What the hell to the temperature of room? Are you gone completely crazy? Why you increased from room temperature to 40? I lost my 12 seconds. You have to compensate. Okay, I'm decreasing my temperature. This is what room conversation. This is what the room temperature. This is what the surrounding temperature of the room is saying. I'm decreasing. Okay. Now the value decreases beyond the room temperature at 20. Now it is okay. All well. Yes, sure. Thank you. But you didn't compensate fully. I lost by 12 seconds and I only gained 4. What about the remaining 8, man? See this, guys. These people. See this. They use we. See this, guys. See. Right? Okay. So what was the actual temperature? What was the actual room temperature? Where the pendulum was showing the exact value of the time period without any error. So let's give you all a minute to solve this question. Come on, everyone. Right, and a minute. Come on, everyone, guys. You can. Come on. We have to just find the temperature. Okay. See, in the beginning of the session, we moved on to the easy. When we move on to the, we'll increase the level of the question slowly. Right. Okay. When by end of the session, the level of the questions will get completely increased and will reach to the deeper. Right. Okay, the level of the question will increase and will reach to the deeper of the concept, and our fundamentals relevant related to those topics will be quite clear. Okay. So now room temperature, the surrounding temperature and pendulum, you should both should get. We are going to solve this sum. Okay. So now less than 7 seconds the remaining one, everyone. It was just the fun part. Please don't consider me as a mad. Okay, right? Because if any physics educator is trying to explain, any physics educator who is really representing the physics well, right? Many educators are there in our PWT, right? So then they can go completely mad for you all to explain those things in front, right? And then they can go completely mad. Anything they can do, right? Even right, we can do bhangra also, right? Okay, not to for fun, right? To explain in the physics how, right? It will come into our regular lecture. Many things we are planning. Okay, slowly, the surprises will get right revealed. Okay, now let's move on to this question. So first of all, I want to ask you all, what will be the time period, the equation of the time period of the pendulum? Can I write it as T is equal to 2 pi under root of L by G? T is equal to 2 pi under root of L by G. Now I want to ask you all with degree why? Why? As I said, now physics entirely things depends on the two part. Why? Suppose. Why? Suppose. Why? Suppose. Why? The time period is changing, temperature is increasing and decreasing. So with increasing, decreasing temperature, which physical quantity is getting completely affected? And because of that, the time period is getting changed. So I must say the intermediate physical quantity is a length. With increase in the length, with increase in the temperature, the length is getting affected. With increase in the temperature, the length is getting affected. Right? With increase in the temperature, what? The length is getting affected. In this case, I want to tell you all, can I write it as delta T by T, and that is equal to half delta L by equation number 1. Now, let us move on to the further solution. Suppose this is the pendulum, and that is having the bob connected. Okay, this is the initial length. Now, suppose the temperature is increasing, right? So, can I say the length of the pendulum? It is increasing a bit. So, this will be the delta L, right? And here comes the expansions of the solids, right? This increase in length to the original length, it is directly proportional to delta T. And here, removing this proportionality sign and getting one constant, that is alpha, that is known as the coefficient of the linear expansion, right? Okay, this T stands for temperature, right? That T stands for time. This T stands for temperature. If you want to change it, we can, right? We can say it as a right delta theta also, right? We can change it as delta theta. Right? Because we are having the two same similar symbols, like two similar symbols now, right? So here, can I consider this as equation number 2, replacing 2 in 1? Replacing 2 in 1, what we get? Delta T by T, that is equal to half alpha delta theta. Now, at 40, beyond room, we are losing 12 seconds. Losing 12 seconds means what? If I'm having 10, I'm spending 5. Right. So what I lost? 5. Delta T. The difference between, right, the remaining and that one. What I lost? 12. So that delta T will be 12. Nah? What I gain? 4. So that is the difference. The gain and loss, it is the kind of a difference. Nah? It's a very simple. Nah? You can consider profit and loss. You can compare this thing to the profit and loss. The gain, lose. Right? Difference. So if I am losing 12 seconds, it means my delta T value is 12 seconds. Right? And that is equal to alpha by 2. Now what will be the theta? 40 minus theta. Consider this as equation number. Consider this as equation number. Okay. What about if we are moving, right? What about if we are, okay, if we are moving beyond the room temperature, we gain 4 seconds. Theta minus 20. Right? While moving at the temperature of 20 degrees centigrade, we are gaining 4 seconds. Right? We are gaining 4 seconds. So this will be the fourth equation. This will be the fourth equation. Now, what will be taking ratio of 3 to 4? Okay, now there is one difference where students might get confused here. We wrote 40 minus theta here, right? We wrote theta minus 20. Why? Reason, here we lose something, here we gain something. That's why, right? And that's because of the temperature difference. One is beyond and one is below. So one is beyond and one is above the room temperature. Right? So solving this stuff, we get 3 that is equal to 40 minus theta whole divided by theta minus 20. So resolving this, we get theta is equal to 25 degrees centigrade. Obviously, it is nearly to the room. The entire time while solving the question, you said beyond room, above room. Beyond room, above. When finally we got the answer nearly equivalent to the room temperature. Right? Nearly equivalent to the. So the 25 degrees centigrade, that is a perfect answer for this specific question. Right? 25 degrees centigrade is the perfect answer for this specific question. Now what we learned, right? We learned a very awesome thing related to the expansions of the solids. Right? First theory related to the expansions of the solid, that is a linear expansion. Okay, I'm moving on. Suppose This is the length of the rod, right? At temperature T. Suppose temperature is increased to, right, delta T. Right? Temperature is increased to delta T. So there will be increase into the length. Right? So this ratio of delta L by L is directly proportional to delta T. And removing this proportionality sign, delta L by L, that is equal to alpha delta T, where the value of the alpha is the coefficient of the linear expansion. Right? Alpha is what? Coefficient of linear expansion. Right? Alpha is what? The coefficient of linear expansion. Now, similarly, if I'm talking about the 2D object, right, then we are having the coefficient of the linear expansion like this way. We are having the coefficient of area expansion. For that, let us take an example. Second topic, right? Expansion. Suppose this is having length L, this is having breadth B. Okay, now suppose this is increasing with respect to temperature, right? Like this way. Right? Okay. Now the entire thing we got L plus delta L, and we got B plus delta B. Right? So in this case, delta A by A, that is directly proportional to again delta T. Right? So delta A by A, that is equal to beta delta T. Right? Then beta is coefficient, right? Coefficient of area expansion. Right? Beta is what? Alpha what? Coefficient of linear expansion. Third, volume. Right? Increase in volume. What? Let us take an example. This is a cube. Right? The volume of the cube is increasing. Right? The volume of the cube is completely increasing. Right? Volume of the cube is getting increased. So what will happen? We are having the delta V by V, that is directly proportional to 3. So that is delta V by V, that is equivalent to gamma delta T, where gamma is, right, coefficient of volume expansion. Many words, many technical words are used into the different resources. Right? We are not moving up to that part. Right? We are not moving in that much detail, but we wrote. Okay. Expansion, linear expansion, area expansion, volume expansion. Right? Expansions. Right? First, we moved on to the different laws of the radiation. We see the Stephen's law, Gain's displacement law, something related to the Kirchhoff law. Right? Second, we moved on with the linear expansion, volume, area expansion, and volume expansion. Right? And we have already seen there is one relation also. What? Gamma is equal to 3 alpha. Similarly, beta is equal to 2 of alpha, right? Okay, for Q. Okay, generally, from theoretically point of view, we are taking, right, this relation valid for all questions. Generally, it differs. It differs, right? It differs, but difference is quite negligible, and we are avoiding it. And for all of those concepts, generally, we are taking this relation as valid. Right. From theoretical point of view, we are taking this relation as well, and we are going to use it to the upcoming questions also. Right. So hope so this thing is completely clear in front of you all. Right. This thing is. Let's move on to the next question. The something that we are combining with solids. Some concept of thermal physics we are combining, some concepts of expansion. See, first we compared the expansion to the time period. Then we compared the expansion to what? Sorry, I think yes. First we compared. So this was okay. This was the radiant energy. First we compared the expansions to the time period in this question. Now we are going to compare the expansions, right, the linear and all of those expansions with the some concepts of solids, some of the modulus of the solids, right? And this is going to be the really exciting question, and really we are going to get a new thing from it, right? Really we are going to get a new thing from, let's see. An external pressure P is applied on a cube at 0 degrees centigrade. One cube is kept at 0 degrees centigrade and pressure is applied. That is equally pressure is applied in such a way that cube is seen. You can see in this visual, right? The cube is equally compressing from all sides, right? Cube is equally compressing from all sides. Right? If K is the bulk modulus of the material and alpha A is the alpha or A, it is the coefficient of linear expansion, right? Then which of the relation states correct for the change in volume? If its original value changes, right, by heating, then we have to select the correct. We have to select the correct relation, right, for the temperature. The change in temperature will be raised by. Okay. So let's give you all a minute to solve this question, and we are going to deal with this concept. Right? Come on. Less than half time is remaining in sorry. Okay, see some questions, some students might having like those who are new, they are. Then we can even pause the video. Then why you all are giving me a minute to solve? We can even pause the video, but many times I've given the explanation. I want you all to solve with me, right? So that will obviously increase the speed, accuracy, and command over the subject. Boom, 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 boom. Okay. Very, very simple thing. Right. In question, it is mentioned about a cube. Right. Suppose, if cube is compressed. Right. Let us take an example. Suppose this is a cube. Right. Suppose this is a cube that is having length L. Now it is getting compressed equally from all sides, and obviously, this is a three-dimensional object, right? If it is getting compressed, volumetric strain will get produced, right? Volumetric strain will get produced that we are defining as delta P by whatever nature of the force it is getting compressed, right? We are not determined, we are not bounded by, right, the source that is applying a force and creating the pressure and trying to change the configuration of the cube. No, right? We are not bounded by the source. Source can be of any part, any way, anything, any whatever it should be. From any source, any kind of source, the force can be applied and pressure can be imparted. Now here the volume is decreasing. So can I say volumetric stress that is negative delta V? Now, what is the definition of the bulk modulus? The bulk modulus states that, right, change in pressure whole divided by volumetric stress that is delta V by V. This is the definition of the bulk modulus. Right? This is what we have seen in solids, but right here, whatever the things are getting changed, it is as because of the change in temperature. Here, the things, whatever they are getting changed, they are changing as because of the temperature. So, can I say this is equation number 1? As things are getting changed as because of the temperature. So, as of concept, what concept? What we can say? Expansions of the volumetric expansions of the solids, right? Okay, the volume of cube is decreasing, right? S of delta T. So can I write it as what? Delta V by V, that is equal to gamma delta T. Can I consider this as equation number 2? Right now I'm ignoring the negative sign because this negative sign is of the compression. Right? Okay, right now I'm ignoring it. Even if you don't want to ignore, then you can write it here also. It's not a big deal. Now replace 2 in 1. Right? You will get bulk modulus, that is equal to delta P whole divided by, right, gamma delta T. Right? So it will be delta T, that is equal to delta P whole divided by beta. The value of the beta is K, that is gamma. But as we have seen, what we need an answer in terms of alpha. But in that situation, we are having the coefficient of volume expansion. But we need in the right. But we need what? We need right the answer in alpha. Okay. So we are just going to replace it. So we get the change in temperature. Right. We are going to replace. Yeah. Delta T, that will be equivalent to P whole divided by 3 alpha. This will be the change in temperature and the perfect answer for this question. Right? The change in temperature and the perfect answer for this specific question. P by 3 alpha K. The C is the perfect answer. So what a new thing we got from this question? What a new thing we got from this question? The concepts of solids. Questions can be created by combining the concepts of solids and thermal physics. So whatever the amount of the modulus you have seen into the solids, na? In solids we have seen that if configuration is getting changed, right, then stresses and strains are produced. But all of those things if are happening is because of change in temperature, then obviously thermal physics is going to play a role, right? In solids we have seen na, right? Okay, there is a change in length of the rod, right? There is a change in the length of the rod. We have seen already, it's not a big deal, right? We have seen that. But if the change is happening as because of the change in temperature and heat supply, then yes, thermal physics is going to play the important role, right? The thermal physics is going to play the important role in. This was the model of the thing, right? We have already seen. Okay, and one thing, again, I'm writing down. Gamma, that is equal to 2 alpha, right? Where gamma is coefficient of volume expansion. Especially for cubes, you can remember, right? Especially for cube, you can remember. And second, that is alpha, coefficient of linear expansion. Right? Similarly, there is another relation, beta, that is equal to 2 alpha. Right? Beta is coefficient of linear expansion. Okay. Hope so. This concept is completely clear in front of you all, and moving forward to the next question. Next most important concept. Generally from thermal physics, the question based on principle of calorimetry. Ice is mixed with water, water mixed with steam, ice is mixed with steel. Sir, every time this kind of the questions are coming in JEE examinations also, sometimes in NEET also, but in boards they are shortly asked, sir, what to do? We are not able to solve, we are not able to grab the actual concept. We are going to discuss because this question contains, right, muscle logic, the sensible logic, right? This question contains the quite sensible logic. First of all, let's see. I'll give you a minute to solve. We will provide a solution. We'll see. We'll solve this here only, right? And then we'll see the concept. A copper ball of mass 100 kg is at the temperature T. Copper ball is at the temperature T. Mass of the copper ball is 100. Now brought into the copper calorimeter of the mass 100 gram. You can see in this visual, right? You can see in this visual. Right? I think this hold on. This visual has been paused. Paused. See, this is. Let us take this is in copper mass. I'm sorry, sorry. Suppose this is the ball. Like this is the ball. Now, how this is taken? First of all, it is heated to temperature T. Now it is kept into the copper calorimeter that contains water. Right. This is what the visual relevant to the question it is given in front. Okay. This copper calorimeter has 170 gram of water at the room temperature. Subsequently, the temperature of the system is found to be the final temperature of the system is found to be 75. Room temperature is 30. Specific heat of the copper is also given. Right now, we have to find the value of. Well, it is based on a very simple law principle of calorimetry. Don't get so much worried. We are going to discuss it live here only, right? And you are really going to enjoy. Just stay till end, be consistent till end. Will clear the concept. First of all, let's give you all a minute to solve this question, right? Come on, everyone. Yeah. I thought the timer is begun, but really sorry for that. Come on, guys, you can solve this. You are having very less amount of the time. Less than half time is remaining. It's a very good question. It is complete. First, we are going to solve this question and we'll see the concept of principle of calorimetry in detail. Right? We are going to see the concept of principle of calorimetry in detail. See, whenever we are having this kind of the question, there is always exchange of heat between two. The one who is at the higher temperature, it is going to lose some amount of the heat to reach up to the final equilibrium state. The one that is having at the lower temperature, it is going to gain some amount of the heat, right, to increase its temperature and reach up to the equilibrium state. Again, I am repeating and highlighting this statement with the quotes, right? A double quote that the one who is at the higher temperature, see, this is at the higher and this is the lower, right? The higher is releasing some amount of the heat to be at the equilibrium state, right? And the lower is gaining the same amount of the heat, right? The lower is gaining the same amount of the heat that has been released by higher, and it is reaching to the same temperature, the same final state. And finally, when equilibrium, the thermal equilibrium is attained, right? And there is no heat exchange between either of the objects. In this case, suppose we are having some statements, right? Ice is mixed with water, right? Water is mixed with the water at the higher temperature. Water is mixed with the steam. Ice is mixed with the steam. Lots of these things may come up. In all of those, right, we have to use the principle of calorimetry. what it states, right? It states that, right? What it states? It states that heat loss by one. This is the first step. Okay, first of all, we are going to directly solve this question. We have discussed this theory, right? Heat lost by first is equal to heat gained by second. Heat lost by first, that is equivalent to heat gained by second. Now in this case, obviously, the copper is dipped into the water in the solution, right? Copper is dipped into the solution. You can see now, right? The copper ball is dipped into this solution, right? It means the copper is at the higher temperature, right? This thing, they are at the lower temperature, and it is already mentioned, right? They are at the room temperature. Initially, they were at the room temperature. The final temperature of the system is 75 degrees. 75 degree, it means that at 75 degree, thermal equilibrium in the system has been attained. At 75 degree, thermal equilibrium in the system has been attained. And after that, no heat exchange will take place between the copper and all of those. So here, who is losing heat? Copper. Who is gaining heat? Water. No. Who is losing heat? Copper. Who is gaining heat? Water and calorimeter. Is mentioned now. There is a presence of calorimeter. Calorimeter is also having its water equivalent. Right? This kind of the terms you've already seen. Right? This kind of the terms you have already seen. It is also having its water equivalent. If it is given the mass, right? See, separately for calorimeter, two words are used. If it is given as water equivalent of calorimeter is this, then specific heat of the calorimeter we have to take as a compare as equivalent to water. If this water equivalent word is used. If for a calorimeter, if it is not used, then separately the specific heat of the calorimeter is used. In this thing, we are moving to the second case. Right? No water equivalent is given. Water equivalent is something else. Right? We are not going to detail and discuss that in detail. Now, so here heat loss by copper, that is equal to heat gain by water plus calorimeter. Right? Water plus calorimeter. Now let's move on to see what is the amount of the heat loss by the copper. Mass of copper ball, specific heat of the copper ball, right? It was at the temperature T and reaching to the final temperature of the system 75. So this is the amount of the heat that has been lost by copper to reach the final equilibrium, the final state. So in reaching the final state, right, the same amount of the heat that has been lost by copper ball, it was received by water and calorimeter. Water and calorimeter both. Right? So what will happen here? So this will be mass of water, specific heat of water, right? They are reaching from the temperature 30 to 75, right? Minus 75. This will be inverse because one is gaining heat and second is right. This will be 75 minus 30 plus for calorimeter, mass of calorimeter, specific heat of the calorimeter 75 minus 30. So this is an important equation. This is the loss, this is the gain. One is loss, one is gain. Okay. Now we are going to replace all of those values and get the answer, right? What is the mass of copper? 100 gram, right? 100 and 170. So this will be 100 into specific heat is 0.1 E minus 75, and that is equivalent to what? Mass of water is 100. Okay, into specific heat of the water is what? 0.1. Okay, specific heat of the water is 1. Oh, water is 170. Sorry, right? Water is 170. Right? Water is 170. So 170. Sorry. Okay. 170 into 1, right? Into 75 minus 30, right? That is 45 plus 100 into 0.1 into 45, right? Okay. So by resolving this, right, see, first of all, let's check the data, whatever it is given. If you're replacing this into the Kelvin, it's okay. If you're replacing this, right, you'll get 85 degrees centigrade. 5 degrees centigrade. Initially, the copper was at that much temperature, 885. When it was mixed completely with this much amount of the water, then right, it will reach finally to the. Okay, so approximately it is 885. It's 170, 45. Yes. It is going to be 885. And 885 approximately. Okay, so what will be the initial temperature of the copper? The D will be the perfect answer for this specific question. Right? D will be the perfect answer for this specific question. Now, what the new thing we got from this? That's the principle of calorimetry. Right? Principle of calorimetry. Right? Okay, heat lost by one, that is the same amount of heat gained by another. Heat lost by one, that is the same amount of the heat. That is the new thing this we got. Actually, you are completely aware of this, but always you get confused. See, if I'm going to give you all the question that ice is mixed with water or steam is mixed with water, then it is quite easy. You can easily apply this kind of stuff. But here comes the calorimeter, because in JEE and KVPY, this kind of the competitive examinations, right? Okay, there is always the presence of calorimeter. And this is where the student starts. I can easily place the question, right? Water is at 40 degrees centigrade, ice is at minus 5 degrees centigrade, right? M1, M2 mass is given, just find the final temperature of the system. You are able to solve it also. But why? Why I kept this question? Why I kept the question of calorimeter? Right? If we are going to climb, if we are going to climb the Mount Everest, then definitely we are easily going to move on for Vaishno Devi Yatra, right? Easily, because you already have the experience to climb Mount Everest. Huh? At least you have the experience to climb up to the Kanchenjunga also, nah? Then easily you can go for Amarnath Yatra and lots of this stuff. And this is just for an example, right? We don't have to include this kind of stuff. This is just for an example. So same thing. The higher question of the calorimeter I kept in front, right? The higher question of the calorimeter I kept in front. So in that, all of the basics and the fundamental concepts, right, they got cleared in by single question. So that's the power of research. When I was analyzing all of those parts, I decided this question I have to keep. Why? Because this is this contains a very fundamental and very senseful logic that will help students to clear their, right? Now, let's move back to the next question. Again. See the flow of the session, man. We see the question related to radiation, then we compare the linear expansion to the equation of the pendulum, right? Slowly, we moved on to the expansion, right? We compared the coefficients of the expansions with the bulk modulus and stresses and strain. How we are going to correlate the Hooke's law with the thermal physics, guys? This is the thing. Right. We have see more than an hour of the lecture has been crossed. Right. In thermal physics, we are stuck to two most important parts. See, 2 to 3 important parts are there. 2 to 3 important fundamentals. Right. Rate of the heat flow. Right. Newton's law, that is a part of a rate of heat flow. Right. And these two things, principle of calorimetry and coefficients. How we are comparing the coefficients to the concepts of Hooke's law. This question we are going to see with the awesome video. The pressure that has been applied to the ends of the steel wire of length 10 centimeter to keep its length constant, but temperature is raised by 100 degrees. Let's give you all a minute to solve this question, right? And we are going to discuss the solution here only. Hope you are guys enjoying a lot, right? Yeah, I hope so. You are getting deeper into the concepts, and thanks a lot for your cooperation and time. Okay, time's up, guys. Boom, boom. By using this, by seeing this chapter, guys, really, I want to tell you all. Okay. Fun the part, guys. Really fun the part. But. You can understand, yeah. We covered up the solids also. Right? We saw the equation of the pendulum also. So I'm really finding proud of my research that yes, something good I kept in front of you. Let me really think right as what I am thinking now. Right? So you can even write all of those into the comment box. You can shower your love into the comment box beneath the video. Right? Now let's see this question come up. See the pressure that has been applied to the ends of the seal. Okay, see. This is the steel wire. Okay. Let us take an example. This is the length L. It is the length of the steel wire. Right? L. That is the length of the steel wire. Y is the Young's modulus. In Hooke's law, we have seen by anyhow if we are feeling an expansion, right? If we are right observing an expansion in solids, right, any solid, right, they shows the elastic behavior, and we are finding any kind of a expansion, right? Then in that case, expansion or compression up to certain proportionality limit, up to certain proportionality limit, we are finding up to certain proportionality limit, we are finding the stress is directly proportional to strain. But while seeing that Hooke's law, we never imagine why this elongation is happening, why this compression is happening, why, what is the source of it. It is as because of change in temperature. It is as because of the mechanical force applied. I'm stretching the object. It means I'm applying a mechanical force. I'm changing the temperature of the object as because of that also the length is increasing. It means I'm not applying a mechanical force. Indirectly, the change in temperature results the change in length. Change in temperature results the change in, right. So here, what the Hooke's law states that, right? The Hooke's law states that the stress is directly proportional to strain. So it means that force per unit area, that is stress, is equal to Young's modulus of strain delta L by L, right? In that law, we want to identify the reason of this delta L by L. In solids, we were comparing it to the mechanical force applied and the length of the object was getting changed. In thermal physics, we are comparing, we are determining the reason for delta. It is just because of change in temperature. So I am replacing Y delta L by L, that is equal to pressure. Right now we can consider it as the pressure because whenever the heat is applied, it is applied. There is a difference between pressure and stress. This is stress. This is pressure. From all sides pressure. This is stress per unit cross section area. Conceptually they are different, right? Okay, now Can I replace y as alpha delta t? Right. So what is the value of y? 2 into 10 to the power 11. What is the value of alpha? 1.1 into 10 to the power minus 5. What is the amount of the temperature that is getting changed by 100 degree? We are getting the pressure as 2.2 into 10 to the power 8 Pascal. The awesomeness of the concept lies behind the changing delta L by L. We have already seen the expansions of the solids, right? And that's because of change in temperature. So that is just because of the change in temperature. See, this is what an awesomeness of the concept is, right? You can understand what kind of the research I am doing in front, right? Okay. So here, 2.2 into 10 to the power 8. C is the perfect answer for this specific question. Right? C is the perfect answer. See, one visual is there in front of you. You can see this. Come on, guys. Sorry, I didn't show. I kept the visual also, but I didn't show it in front of you all. I kept the visual also, but I didn't show it in front of you all. Right? See. Right? You can see. And see, this is heat is supplying. And see, you can see the increase in the length as because of this heat supply or this heat supply, whatever we are supplying, right? That will result in change in temperature, and this temperature change in temperature, it is going to increase in the length. Where Hooke's law doesn't up to certain, but they are having the limitation. They already said up to certain proportionality limit. It doesn't mean that only mechanical force is going to apply, right? And we are going to observe the change in length. No. Okay. Now, what concept we got from this question, guys? What concept we got from this question? First of all, Hooke's law. It is very simple thing. Right? Up to certain proportionality limit. Stress is directly proportional to strain. It means that the stress versus strain graph up to certain proportionality limit. See, practically it is not straight. Theoretically, we are taking it as a straight. And some of the reference book awesome thing is given. Practically, it is also not straight. If I'm talking about real practicals, now it's like that way. Not exactly straight, but theoretically, we are taking as sigma is directly proportional to. Okay, and the slope is Young's modulus. Slope is what? Young's modulus. And related to delta L by L, that is equal to alpha delta T, that is coefficient. Alpha is the coefficient of linear expansion and linear expansion of the solid. This theory we have already seen before, right? And we have combined these two and created new awesome fundamentals. Right? If the person who is teaching physics in front of you all now, if he is getting excited of his own research now, right? Okay. If he is getting excited of his own research now, then definitely he is going to get a maximum amount of the energy. He is going to get maximum energized while dealing with you all while teaching. And when this happens now, right, it means teacher is in maximum mood to teach physics, right? And you all are right in mood, right, to learn physics. So that kind of resonance is obtained. I'm something delivering in front of you, right? Your frequency is matching with me, resonance, because I am showing up my maximum energy in my maximum research, right? That's all. A thermodynamic system is taken through the cyclic process. The net work done by system is we are going to apply the shortcut, right? Because area under the PV graph, you all are completely aware of it, but from this question we are going to see something new. So let's first of all, there is a shortcut also, there is a long cut also, but we are going to solve this by a shortcut, right? So let's have you all a minute so you can solve this question and we'll see the solution here. Man, let me produce some strain in my body, right? Okay, let me stretch myself. We used to say that let me stretch myself and to gain the enormous amount of the energy. But in this case, I feel like dancing la 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 la. Right? And the one who is teaching physics is enjoying. The student who are learning, they used to get enjoy. Oh, sir, we are on the seventh heaven. Right? It's a very simple question. That's why you are not going to write what we can say. We are not going to consume maximum amount of the time. Right. See, area under the PV graph shows, but this is a cyclic process. Right. This is the cyclic process, and in the cyclic process, see, there are some conventions. Right. In between physics and chemistry, there are some conventions that differs. There are some conventions that differs. What are those conventions we are going to see? The thermodynamic system is taken through this. See, it is a PV graph. Wallah, wallah, Habibi. Our question is solved, right? If it is a PV graph, right, it is a cyclic process, then there are only three cases, and all of those three cases are having direct formulas. I'm going to give in front of you, right? If it is a PV graph, it is a cyclic process, then we are having the three shortcuts. Three shortcuts I am going in front of you. We are going to discuss. We are going to apply direct formula, replace all of those values. Get it. So suppose this is the amount of the area, right? The process is covering. Okay, so first of all, I want to tell you all area under PV curve. Area under PV curve. What? It's work done. Area under the PV curve shows the work done. Right? Area under the PV curve shows the work done. So it's a very simple thing. Work done. It is a rectangle, so it will be length into breadth. This is 300 minus 100, 200 cc. This is 200 minus 100. That is 100 kilopascal. So it means that 200 cc into 10 to the power minus 6. If I am converting 200 cc, that is equal to 200 into 10 to the power minus 6 meter cube. Right? 100 into 10 to the power. Right? 100 into 10 to the power kilopascal is 3. So here work done. That is equal to 20 joule. But my answer will be negative. Process, you can see this process, right? You can see this process. Generally, right, that differs. Okay, generally that differs. Okay, see here there will be the great confusion into the sign convention. Right here there will be the great confusion into the sign convention. That's why I'm removing the work. The net work done is 20 joule. Right, the net work done is 20 joule. The most important thing related to this concept is sign convention. Right? Why I didn't told anything about the sign convention, right? Because there is a difference in physics and chemistry. Whenever you are dealing with the thermodynamics in the chemistry, some students have been taught to deal with the process as a clockwise and anti-clockwise. Some are taking as the clockwise as positive, some are taking as the anti-clockwise and negative, some are confused in between physics and chemistry, what kind of the thing is going on. So let's leave all of those stuff, right? Okay. Let's leave all of those stuff first of all. Work done by the system. By positive. Work done by positive. On heat supply positive. For physics point of view, this is the general way. Heat release work done by positive, right? Work done on negative. Heat release negative, heat supply positive. Now, this is the sign convention, and immediately I'm going to rub, right? Because it's not a big deal, because it's already in the question it has been mentioned, right? Already, I'm sorry, yes. Already in this question it has been mentioned what? Already in this question is work done, the net work done by the system, right? It is already being mentioned. So we are not going to into the depths of the sign conventions right now. We got our answer as a 22. Right? Now, three important shortcuts I'm going to write here. If it is PV graph, if it is a cyclic process, then there are three shortcuts. First, because whatever I'm writing this in front of you all now, this thing you are going to use directly in our next questions. Right? See. Suppose this is the PV graph. We are having a rectangle, right? V1, V2. This is P1. So here the work done will be, what will be the work done? See, right now I'm not moving that process is going on the clockwise or anti-clockwise, right? Everything will be mentioned. Right now we are moving on with the shortcuts. Right? Right now we are moving on with the shortcuts. Okay. So this work done will be what? Length into bracket P1 minus P2. That is V1 minus P2. If we replace those values now, I'm sorry, it will be V2 minus V1. P1 and P2 minus P2. Right? Okay. Suppose process is going like this way clockwise, right? Then definitely you are going to get the negative volume. Suppose the process is going anti-clockwise. Obviously, the initial volume will be this, the final volume will be this. Definitely, you are going to get automatically the positive, right? So that's why I'm not saying to move on with the conventions right now, right? Because these shortcuts, right, are like that. If it is a clockwise, it is an anti-clockwise. If it is a clockwise, obviously the volume is decreasing and we are going to get the negative. Because work is done on the system and it is compressing. The system is getting compressed, the gas is getting compressed. Anti-clockwise, things differs like this way. So this is the first shortcut. Now let's move on to the second shortcut, right? It is a very important stuff. This is the PV graph. This is another cyclic process. V1, sorry, this will be V1, right? Okay, this will. Right. This will be V1. Right. In some of the lectures, some of the tutors, right, they are saying anti-clockwise take as positive and clockwise, sorry. Yes, anti-clockwise take as positive in physics and clockwise take as negative, right? But my suggestion is to follow the general phenomena work done by heat release supply. My suggestion, right? If you have already reached, see, I'm not delivering you all of these things into the detail right now. Okay, we are doing on like the shortcuts only, right? If it would be the detailed lecture, and then I would be able to prove, because we are having the very less amount of the time you have to complete syllabus also, right? I can prove generally, yes, there is no need of being clockwise and anti-clockwise. Yes, we can identify whether it is bi or on the. But it needs some amount of the time, and we're definitely going to see after whatever, or after this series, whatever it will come, we are definitely going to see. Right? See now. Okay, so here, what is the, see, work done is area under the curve. Area under the graph. So this is the area. What will be the area? Pi r square kind of thing. Pi. Right? One will be P1 minus P2 whole divided by 2. V1 minus V2 whole divided by 2. This is the work done. This is the second shortcut. Third shortcut. Right. Suppose it is a triangle. Then again work done will be half area under triangle. So that will be equivalent to half V2 minus V1. These are the three important shortcuts if the directly in the question it is mentioned. Right, and these shortcuts are really going to be helpful, right? If the question comes in KVPY from this section, right? They are completely aware of what things are going on, right? They might get confused also because in our upcoming questions we are having one P versus T graph also of thermodynamics, and we are going to deal very effectively with them. Right, apart from all of this, okay, but maximum amount of the questions in NEET and everything they are asked from your. Right. So these three are the shortcuts for the PV diagram, right? Next question. Sir, we are going to solve this question immediately because you already gave us the shortcut. No worries. See, ideal gas taken. Okay, one new thing related to the cyclic process we are going to do. One new thing after this question. There is one point remaining, and that is also the fundamentally quite important when we are going to discuss. Come on. I'm giving you a minute to solve this. Come on, everyone. Okay. What is this? 3v minus v 2v. What is this height? 3p minus p 2p. 2p is gonna cancel. Work done. Right? What will be the value of work done? Simple. We are applying the direct formula. Work done that is equal to 2p. That is perfect. Right? Work done that is equivalent to what? 2pv. Right? It's 2pv joule. That is the perfect answer for this specific question. Now let's move forward to the next part. Okay, same shortcut is there. Okay. Aha. One new thing apart from the work done, right? Relevant to this. Okay. NCP and CV. Right? It is there in front. Let's see this question. And we are having one relevant visual in front. Okay. 40 calories of heat is needed to raise the temperature of 1 mole of an ideal gas. In this cube, let us take an example. 1 mole of ideal gas is present. 40 calories of heat is needed to change its temperature from 20 to 30. Then amount of the heat needed to raise its temperature over the same interval at the constant volume. At the constant volume. Right. It's okay. Let's give you all a minute to solve this question. Come on, everyone. Pain. 9, 38. 37, 36. Guys, you can even solve in a minute. You can pause the video also. As usual, I used to say in all of my sessions that I want you all to solve this question, right? I want you all to solve this question, right? So that you can increase your speed, right? You can increase your accuracy and obviously the command over the subject. Okay, come on everyone, guys. First of all, it's a very simple question. See, one misconception that students are having. Wrong. Q is never equivalent to NCP delta. And Q is always equivalent to NC delta T. Fundamentally, just keep this thing in your mind. This is the correct one. Q is always equivalent to NC delta T. It is never equivalent to NCP delta T. But if anything is going at the constant pressure, then we are writing this equation. If anything is going at the constant volume, work done is zero, then according to the first law of thermodynamics, we are going to write Q as delta W. The general statement is this, and then it varies, right, depending on an application. So in this case, what it has been told, 40 calories needed, right, number of moles, right, NCP delta T, right, NCP delta T, right, at constant pressure, 40 calorie T is needed to increase the temperature of 1 mole of gas by 20 to 30. From 20 to 30 it means 10. So we are getting the value of CP as 4. Cp minus Cv, that will be equivalent to R. So from this we will get the value of the Cv as 2.4. Right? Okay. So value of the R is given as 2, na? Right, yes. R is given as 2. So obviously we are going to get as 2 only. Right? Nearly equivalent to 2 because value of the R is given as 2. See, 2 calorie per mole calorie. Right? 2 calorie per mole. 2 calorie per mole calorie. Right? Now we got this value of the Cv. Now we need to see for constant volume work done is 0. So according to the first law of thermodynamics, Q is equal to delta U. So can I get Q is equal to NCV delta U. Same 1 mole, same 2 temperature, 20 calorie of heat is needed. First is the perfect answer for this. Right? First is a perfect answer for this question. What do you think we got from this? Right? First law of thermodynamics. First law of thermodynamics. What it states, right? First law of thermodynamics. What it states, Q, whatever the heat is supplied, right? Some part of heat will change the W and rest of the part will do the work. Right? The amount of the heat supplied, some part of heat, right, will replace what will change the internal configuration of the system in the form of delta U and some will do the work. Okay, so now in this case, what will happen? Right, the first law of thermodynamics. Right, first law of thermodynamics, Q is equal to delta U plus W. Right? Delta U is always an internal energy and CV delta T. Right? Okay, because it is associated with the internal configuration of system. Now we are in 4 processes. First, isothermal process. Right? Because we have already discussed the first law of thermodynamics. I think it is best time. Okay, I think it is best time to discuss rapidly about the 4 of these processes. Temperature is constant. Right, delta U will be 0. Right, whatever it will be Q, that will be what we can say the work done. Second, isobaric process. Pressure is kept constant. Right, Q is equal to delta U plus W, right? Here work done, that will be is equal to NR delta T. Right? This is something related to the isobaric process. Adiabatic, net heat flow is 0. It means that whatever amount of the negative delta W, it is only the work done by the system. Right? This is the third process, adiabatic, and here work done it is given as P1 V1 minus P2 V2, right? Whole divided by gamma minus 1. Equation of the adiabatic process is PV raised to gamma is equal to constant. For isochoric process, right? Right, volume is kept constant, work done is 0. Whatever amount of the Q is there, that will be equivalent to delta U. Right? Whatever amount of the Q is there, that will be already equivalent to, right, delta U. Okay, here PV is equal to constant. Right? So this is all of the stuff we got. Right? Rapidly we are going because we are not having that much amount of the time to go on into the details. Okay. Often graph again, you have to follow the first law of thermodynamics. See, this kind of the graphical questions will also arise, right? And we have to see the first law of thermodynamics. See, as usual, I said that we are not going to follow the quantitative approach, we are going to follow the qualitative approach. Right? We are not going to follow the quantitative, we are going to follow the qualitative approach. We will see 10 to 15 amount of these, and we not have to see 40, 15 to 1, no. 10 to 15 amount of the some are very efficiently, very effectively, in a very detailed manner. Right? Let's see. A cyclic process ABCD is shown into the following PV diagram. Which of the following curves represents the state process? For this PV, you have to select the correct PD. Right? Let's give you all a minute to solve this question. Come on, everyone. This PV graph is given. Then we will move on, like we will solve this question step by step and we'll decide. Because in this phenomena, all of the four processes are going to come. PT graph. Right. First, let's move on to from A to B. Let's move on from A to B. You can see A to B process states that pressure of the system is kept completely constant. Pressure of the system is kept completely constant. It means that A to B will be like this way. This is A. Right. Pressure is kept constant. Now, so A to B, it is a kind of which process? It is an isobaric process. See, now I am not going to discuss any theoretical part about this thermodynamic processes. Because you already see what is an isobaric, choric, adiabatic, right? And this isothermal, everything you have seen. You have seen in your regular lectures also. This is just a glimpse and how to solve the question. As usual, we are following the reverse engineering. So this is what moving on from A to B. Now, from B to C, you can see. It is the PV graph. Right? Okay. PV graph, this states that it is an isothermal process. Right? For isothermal process, let us move on from B to C. Right? Why I am saying it is an isothermal process? Right? Okay, because for isothermal process, PV is equal to constant and P is inversely proportional to V. P is increasing, V is decreasing, V is increasing, P is decreasing. That's why for isothermal process the graph is like this way, and for isothermal process temperature of the system is kept constant. Temperature is constant now, right? And you can see pressure is decreasing. Here it is the value of the P1, right? Here we are valuing the value of P dash. Pressure is decreasing while moving on from P to D. Right? It means volume is increasing, expansion is going on. Right? This is an actual method to determine what is an expansion, what is the compression. See, here the pressure is decreasing now. Pressure is inversely proportional to volume. It means volume is increasing. Pressure decreasing, volume increasing, pressure decreasing, volume increasing. Volume increasing, it means there is a change in the configuration, right? And object is expanding. C to D, again we are having the right volume constant, so it means work done is 0. Right? Now, here. D to a reverse phenomena is going on. Right? D to A, the reverse phenomena is going on. Right? This will be D. Okay, D to A, reverse phenomena is going on. And again D to A, C to D. Right? Okay, this is an isochoric process. Right? In isochoric process, volume is kept constant. Right? Volume is kept completely constant. If volume is constant, then P is directly proportional to T, then we are having the linear graph. If P is directly proportional to T, it means it is following y is equal to mx form. So the graph will be straight line. It is following y is equal to mx, then the graph is a straight line. And again, take the perfect answer. So this is how step to step we solve this question. Right? C to D, again D to A is the same process as like A to B, but into the reverse manner. Right? Now, one new thing about the cyclic process, right? A new thing for a cyclic process, right? As I said before, one thing is remaining that I want to tell you in front of you all, right? The graph of the cyclic. There are the three shortcuts for the graph of the cyclic process. I already showed, but for cyclic process, I want to tell you all. Delta U is 0, right? Delta U is 0. For cyclic process, delta H is. This is the new concept we got it from here. Okay. Now here comes the heat engine, efficiency of the heat engine. This one thing was remaining. We saw the first law of thermodynamics. We saw the different fundamentals of the thermodynamic processes. Right? We saw the graphs of the thermodynamic processes. We saw the principle of calorimetry. We saw the rate of the heat flow. We saw the linear expansion. We compared the linear expansions to the time period. We compared the linear expansions to the Hooke's law. We compared to the linear expansions to the stress and strains. Everything we did. Right now, heat pump and this second law of thermodynamics related one question is remaining. So, mota we have covered. In Hindi, it is said na mota sa we have covered because we are having as usual very less money. After that, right, the most important topics like SHM and waves. Upcoming session will be on SHM and waves. After that, we will move on to the electrostatics. After that, we will move on to the electricity and magnetism. And again, after that, we will move on to the optics, right? Okay, and the remaining part of the physics. We will see. Right? So maximum in KVPY you will get an enormous amount of the content, so that you are easily able to crack all of those stuff, right? Now see, let's see this question. An ideal gas heat engine operates in a Carnot cycle between 227 and 127. It absorbs this much amount of the heat, high temperature. Amount of the heat that is converted into the work will be. Right. So this will be the last question of the session. Come on, everyone. Let's give you all a minute to solve this. Okay, relevant visual related to it is already being shown. Time is up. Okay, I'm extremely sorry. Right, I, as usual, stuck in between my leg. Right, it's quite painful. Right, it is quite painful. Like just it, really painful. Sorry for the interruption that we had. Sorry. See, an ideal gas. Okay. See, first of all, let's simple thing. Efficiency states that 1 minus T of sink, right, by source. What is the temperature of this sink? 127 degrees centigrade. It means that it is 400 by 500. Right. So theta will be what? 100 by 500. That will be 1 by 5. This is an efficiency of the cycle. Right. This is the efficiency of the cycle. Okay. This is 1 by 500. Now, this efficiency, what is the general formula of the efficiency? It is always output by input. Right? What is the general formula? It is always output by input. Whatever the amount of the output you are giving, right, when compared to the input, that defines your efficiency, and efficiency defines your capability to do work. So output is what? Right, the work done by input heat supply. So work done will be 1 by 5 into Q. What is the amount of the Q? Right? Q is 6 into 10 to the power 4. Okay, so this will be 1 by 5 into 6 into 10 to the power 4. So our work done will be 1/5 of this. Right? That is the perfect answer for this question. Okay, the visual related to the Carnot, it is already been shown, and we are going to see this theory very very speedily. We are going to see this theory. Right? See, this is the source, this is the sink. How much it is amount, like how much amount of the is because of the temperature difference between source and sink, it is gaining some amount of the energy and it is giving up to the sink, right? And in between that, as because of higher and lower, some amount of the work is done. Right? This is the water concept of the heat engine. It is right. See, the natural phenomena is going on. Heat engine, right? In the first process, heat engine, the natural phenomena it is going on. Source moves out, right? Something that reaches to sink and work is done. It's done, that is Q1 minus Q2. In a heat engine, we are having the output as work. And this is a natural phenomena. This is at the high temperature. Right? And this is at the low temperature. So this is the kind of the natural phenomena going on. From higher to lower, heat is flowing. Right? Now, the reverse phenomena is of the heat pump. Right? What it states, right? This is a sink, right? This is the source, right? To maintain the sink at the lower temperature, the heat is pumped out. And to pump out the heat, work is done. So that the things may get to, so W1 plus Q1 is equal to Q2. Here we are having efficiency 1 minus T2 by T1, right? Okay. Okay, 1 minus T2 by T1. Here we are having the B, that is coefficient of performance. Right here we are having coefficient of here we are having what? The coefficient of performance. Right? The coefficient of right. Something related to the Carnot engine is also there. I think it's time. So this will be the homework question. Carnot engine you all are aware of, right? Okay. So I want you all to answer this homework question right into the comment box beneath the video. Right. We have seen the enormous concepts of thermal physics, right? Okay, and thermodynamics. Okay. Okay, we moved on very fundamentally. We solved all of those stuffs into the very effective manner. Right. This is the homework question, and I want you all to answer this question within the comment box. Right. Okay. So guys, I think many questions were there, but obviously below, right, beneath the video there is a description in the link. Link in the description. I'm sorry, there is a link in the description from which you can download all of those notes. Right, in notes, some of the questions we haven't solved, so those are kept right for you all to practice. Just practice all those, right? Okay, just practice all of those questions, right? Those who are right relevant to KVPY examination only, and those are kept for all. Right? Because in 2 hours of session, right, I said we have to move on for the qualitative approach, not for the quantitative approach. You can see from the beginning of the session, those who have seen this, right, those who are still, right, seeing this video from beginning, right, so they are really aware of what kind of the stuff they got, what kind of the new things they got, right? Okay, so okay. I think see many questions are there, and you can solve it. It will be available into the PDF. Never just physics book fights cover. It's okay. I've already all the time I'll say it. Okay, guys, it's time to go. Thanks a lot for your cooperation and time. So from units and dimensions, we started with this series on your demand, followed up by a motion in 1D and 2D. In that also, you gave me the awesome response. Right after that, it came the NLM. You gave the right. You shower your love, and then came work energy and power, and then came the rotational motion. Right, and after that we moved on with thermal and thermodynamics. Right now, next will be a completely based on SHM and wave. Right, it is also important from the KVPY exam perspective point of view. Sorry. Right, so guys, it's time to go. Right, again we will come back with this new session and all of those new concepts, the new things in front of you all. And as usual, we'll follow the reverse engineering because we're having less amount of the time. Okay, so it's my request to stay consistent till end, and really you are going to earn a lot in terms of content and knowledge, right? And I will be waiting. See all of those comments beneath the video I'm reading. Yes, it isn't possible to reply all of those, but I'm reading, right? So guys, please definitely shower your love beneath the video and share it maximum as much you can in all of those social media. Share, right? So guys, it's time to go. This is your own favorite educator, Indrajeet Singh, doing as much maximum as much possible for you all. Right? This is Indrajeet Singh signing off from the desk. Bye bye. Sat Sri Akal and Namaste from my side, Bachcha. Bye everyone. Stay at home, stay safe, stay healthy amidst the pandemic.